Welcome to this explainer. Today, we're unlocking the mystery of gravitation. It's that foundational, entirely invisible force that literally orchestrates the entire universe. It's a force we feel every single second of our lives, yet we rarely ever stop to actually think about it. So let's dive right into the history, the science, and the sheer mathematical beauty of gravity.
To really grasp the scale of this, we have to go back to one of the greatest scientific minds of recent times, Sir Isaac Newton. Now, as the famous story goes, Newton notoriously observed an apple falling from a tree, and he asked a simple yet utterly brilliant question. Why does the apple plummet straight down, vertically, rather than flying off sideways or at some weird angle? And maybe more importantly, why does the apple fall while the moon stays perfectly suspended up there in the sky? He realized the Earth had to be pulling the apple toward its center. But could this exact same invisible pull extend all the way out into space? Could it actually reach the moon?
To solve this massive cosmic mystery, we actually need to look at a super simple, everyday action. Newton basically realized that the key to understanding the heavens was right here in the palms of our hands.
Think about this for a second. When you tie a stone to a string and just swing it in a circle above your head, you're constantly pulling that stone back towards your hand, right? If you were to suddenly let go of that string, the stone wouldn't keep circling. No way. It would instantly fly off in a straight line. It only stays in that circular orbit because your hand is actively, constantly yanking it inward.
Well, this is precisely what centripetal force is. It's literally a center-seeking force acting on an object moving in a circle. And Newton's absolute game-changer of a breakthrough was realizing that gravity acts exactly like this invisible string between the Earth and the moon. See, the moon has its own velocity, so it wants to just fly off in a straight line. But the Earth's massive gravitational pull acts as that string, constantly pulling it back inward, creating this beautiful, continuous orbit.
But before Newton could formulate the definitive why behind this invisible string, another total genius, the German astronomer Johannes Kepler, had already figured out the how. And he did it using decades of naked eye observations. Long before telescopes were even a common thing, astronomers had collected a massive amount of data about where the planets were in the sky. So Kepler rigorously analyzed all this raw, chaotic data of the cosmos and established 3 strict mathematical rules, or laws, that dictate exactly how planets move. First, planets don't move in perfect circles. They orbit in ellipses, with the sun sitting off to one side at a focal point. Second, a line from the planet to the sun sweeps equal areas in equal times. And third, the square of the orbital period is proportional to the cube of the mean distance. To really wrap your head around his second law, imagine a planet's path. It actually hits the gas and moves faster when its orbit brings it closer to the sun, and it totally slows down when it's farther away. But the absolute geometry of the cosmos means that the physical area swept by the planet over the exact same amount of time, say exactly 1 month, is perfectly identical, whether it's super near the sun or far from it. Kepler completely mapped the clockwork, but he didn't know what was actually winding the clock.
And that is exactly where Newton stepped back into the picture. Newton took Kepler's incredibly precise astronomical data and unified it with his own theories of centripetal force to create something entirely new, a real paradigm shift.
So the absolutely crucial takeaway here is that Newton discovered gravity isn't just some local earthly phenomenon that makes apples drop on our heads. It is a universal law connecting every single piece of matter in existence. He basically stated, quote, "Every object in the universe attracts every other object with a definite force. The very same force dropping the apple is holding the planets in orbit around the sun."
He even proved this mathematically with an incredibly elegant formula. The force of gravity, F, depends entirely on multiplying the masses of the two objects, so m1 and m2, and then dividing that by the square of the distance between them. And that capital G in the equation, that is the universal gravitational constant, a ridiculously tiny number first experimentally measured by Henry Cavendish. Basically, this formula tells us that if you double the mass of an object, the gravity doubles. But if you double the distance between them, the force drops massively, decreasing by a factor of 4.
Now, if every single object mathematically attracts every other object in the entire universe, let's bring this down to a highly relatable human scale. What does this actually mean for us on a daily basis?
Let's ask a fun question here. Say you've got 2 friends, let's call them Mahendra and Virat, and they're sitting just 1 meter apart on a park bench. If gravity says they must attract each other, why on earth don't they spontaneously slide right across the bench and crash into one another?
Well, let's crunch the numbers real quick. If Mahendra is 75 kilograms and Virat is 80 kilograms, the exact gravitational force actively pulling them together is 4.002 times 10 to the negative 7th newtons. That is 0.0000004 newtons. It is an unimaginably, infinitesimally tiny force.
Because this force is so minuscule, the everyday physical friction from simply sitting on a wooden bench completely overpowers that gravitational pull. Actually, even if we magically removed all the friction in the world, their starting velocity is zero, and the acceleration from that tiny force is so weak it would literally take them ages to move just a single centimeter towards each other. Thankfully, this is exactly why you don't uncontrollably slide into your friends at a dinner table.
Okay, but let's see how this builds when we dramatically increase the mass. What happens when we swap out a human for, say, an entire planet?
When you compare that incredibly tiny gravity between two humans to the massive gravitational pull of the Earth on a human, the difference is absolutely staggering. Because of its immense size, the Earth pulls a 75-kilogram person down with roughly 735 newtons of force. We are talking about a force over 1.8 billion times larger than the attraction between our two friends on that park bench.
It is this overwhelming, gigantic mass of our Earth that not only pulls an apple firmly down to the ground, but successfully acts as that invisible string, reaching hundreds of thousands of miles deep into space, holding our moon in a continuous, perpetual circular orbit.
And you know what's truly wild? This massive cosmic dance doesn't just happen high up in the sky, completely disconnected from us. Just as the Earth pulls on the moon pulls right back on the Earth. And because water is fluid, the moon's gravity physically pulls our oceans toward it, bulging the water outward to create the daily high and low tides we experience on our beaches every single day. The cosmos literally touches our shores.
I want to leave you with this final, kind of mind-bending thought. Gravity might technically be the weakest of the fundamental forces in physics, but it entirely dictates the architecture of the cosmos. So, what would our universe look like if gravity just vanished completely? Everything would fly apart in straight lines, or imagine if the value of that gravitational constant, g, suddenly doubled overnight. The planets would be pulled way closer to the sun, our body weight would double, and life as we know it would fundamentally change forever. It really makes you appreciate that invisible string holding the whole shebang together, doesn't it? Thanks so much for joining me on this explainer. Keep wondering, keep looking up, and I'll catch you next time.